Hello and welcome back to our series exploring the Automated Drone Image Analysis Tool, or ADIAT. My name is Charlie Grove. I'm the Director of Technology for Texas Search and Rescue and the creator of ADIAT. In this video, we're going to take a look at a couple of advanced features that we have in place that can be used in conjunction with our RGB algorithms. With that, let's dive into the first one, which is normalizing histograms.
If you're not familiar with a histogram is a graphical representation of the tonal distribution of a digital image. It shows the frequency of each pixel intensity value in the image, helping to visualize the amount of light and dark pixels. It provides a quick and effective way to understand the exposure, contrast, and dynamic range of the image. It has an X and a Y axis. The X axis represents the range of possible pixel intensity values, and the Y axis represents the frequency or count of pixels for each intensity value. Higher peaks indicate a greater number of pixels at the specified intensity. So, for example, if we look at this image here, we get this histogram and we have this peak right around 150 with the highest frequency. So that's where the highest concentration of pixels are from a total distribution standpoint. Note that nowhere in this definition does it talk about color. Color does not come into play for this type of histogram. So if we took this same image and converted it to grayscale, we would actually get the exact same histogram. So this is all about the exposure, the contrast, and the dynamic range of the image. It isn't impacted by the actual colors. Why is this important to us? So what we have implemented in ADIAT for our RGB algorithms is the ability to normalize histograms. And the reason we want to do that, if we look at this example, we have two pictures of essentially the same area taken only 20 or so minutes apart. The one on the left is taken in full sunlight, and you see the impact of that on the colorization. And the one on the right is taken when it's a little more overcast. The colors are a little more muted. If we want to control the variability of the light, because that's going to control, or that is going to impact the color of what you see on the ground or what is on the ground, we want to be able to normalize those two images to be as close as possible so that we're comparing the same things. As the example, we took a sample color from our landing spot in both of these images, and you see not drastically different, but enough to prove the point here of, hey, different lighting conditions are going to have an impact on the color of objects on the ground. So what we do with histogram normalization is we choose a reference photo and say, I want all of my images to match the histogram of this one. So as a starting point for these two images, we have these two histograms overlaid on each other. Image one is the image on the left, so the pixel values are a little further over towards the bright side. And on image two, which is on the right, concentration is a little bit further down. If we were to normalize image one to make it look as much like image two as possible from a histogram standpoint or from a lighting standpoint, it looks like this. And the color of the sample from the landing spot looks a lot more similar to what we had in image two than we originally had. As you can see, the rest of the background also is a little closer to what we had in image two. So again, all about eliminating variables where possible. In this case, we're eliminating as much variability in lighting conditions as possible. If we're looking to look at the overlay of the two histograms for these two images now, it looks like this. So much closer together, much more consistency in how we can see those two images and now use the same color range or match filter or what have you to analyze those and not having to worry as much about variability in lighting conditions. Let's take a look at what that looks like in ADIAT. So back over in ADIAT now, we have our normalized histogram feature here. If we go ahead and check that box, we can go ahead and select the reference image, and that's going to be our base image from all of our input images that we're going to use and say, hey, let's take all of the other images in this test set or in this image set, and let's match the histogram as closely as possible to this reference image. Once you do that, the rest of the setup is the same. You select your color range the same way you do, or color match, or excuse me, match filter the same way you do before, and then you can go ahead and click start. One thing to note as it goes through and does its analysis here, it will take a little longer because it is going through that process of normalizing the histograms, and the output images that we will get at the end of this process will actually be with the normalized histograms. So it won't match the colorization of the input image exactly because it has been normalized to match that reference image. So we'll let this finish up its run. And we can go ahead and view the results. And just like before, we see similar results where the areas of interest are identified, still matching the color range in this case because that's the algorithm we're using, just with the colors a little more consistent from image to image. So hopefully that's a useful feature for you. It's especially useful in scenarios where you have variability in cloud cover, or you're taking images at different times of day or across multiple days. Just helps eliminate any variability in the colorization due to lighting conditions. The other advanced feature we have in place to utilize alongside the RGB algorithms is called k-means clustering. And what k-means clustering is, it's a classification technique designed to group like data points. For the purposes of image analysis, k-means clustering is used to group similar pixels together in order to reduce the overall number of colors represented in an image. So in the RGB color space, there's 256 possible values for the red channel, 256 for the green channel, and 256 for the blue channel, which means 256 to the third power. There are 16,777,216 possible unique colors in the RGB color space. Sometimes there's just too many colors. We don't need to see a million different shades of brown and green. We can want to simplify the images to maybe 2, 3, 4 shades of brown and shades of green, so we can kind of eliminate those and say those aren't of interest to us. We want to focus on these other areas. As far as how k-means clustering works, I'm not going to read through all of this, but the quick version of it is it's an iterative process where it randomly kind of picks some pixels to start with and starts measuring how far away from that color each of the other colors are. It goes through that process a number of times, sometimes thousands of times, until it says, hey, these are the colors that are best representative of the colors in the image. And what that looks like in practice is if we start with an image like this, which has 422,945 colors, we can very quickly reduce that down to an image like this that has only 50 unique colors. And instead of dealing with an analysis of all 422,000 plus, we are only looking at 50 colors. Let's go ahead and look at what that looks like in ADIAT. All right, back over in ADIAT now. I'm going to go ahead and select my input and output folders for our k-means clustering demo. I will note up front that k-means clustering definitely slows down the analysis process. There's a lot of computation going on and iterations going on behind the scenes to identify the correct clusters for that process. So it is a valuable asset. It is a valuable feature to have in here, but I would suggest using it sparingly. Having said that, we'll go ahead and select our input-output folders. I selected a much smaller input folder. I think there's only 6 images in this one. When we select the use k-means clustering, the only parameter we have to set is the number of clusters, which is the number of colors that we want to include in the output of this. Once I select that, I can go ahead and choose whichever RGB algorithm I prefer. Let's go back to our shade of blue. Now, since we're going to have far fewer colors, I can go ahead and set the color range much wider on this one. Let's do, and we'll not go that crazy. Let's do 100 on all 3 of them. Have that set. and we can go ahead and hit start, and you will see that this starts going through its process just like it normally does. And for each one of these images in our 7 image set, it is going to apply k-means clustering before it applies the color range algorithm. If you happen to be using both histogram normalization and k-means clustering at the same time, just know that the histogram normalization is actually going to be applied before the k-means clustering. So just something to be aware of. Once this completes, we can go ahead and view results, and we see the areas of interest. Again, the image looks very different than it started because we have reduced it down from 400,000 plus colors, however many happen to be in this image, down to 30, I believe is what we set the clusters at for this one. So those 2 areas of interest were identified. They're pretty much the only things in here that aren't a shade of brown or green. Likewise, on this image, we still found at least one of the 2 shirts, and so on and so forth. So if you have images where you're running into issues where there's just way too many shades of brown, shades of green, shades of whatever similar colors are out there, and it's preventing your areas of interest from standing out, we do have that k-means clustering feature available. Now, since both k-means clustering and histogram normalization affect the colorization of images, or the lighting and exposure of images, or the number of colors in an image, neither is applicable to thermal imaging. And that is why, if you go back to our temperature range or temperature anomaly algorithm, those features are in fact hidden. That covers our 2 advanced features that we have available as of version 1.3 in ADIAT. Again, I hope these videos have been helpful to you, and if you have any questions, concerns, thoughts about ADIAT, by all means, please feel free to reach out. Thank you very much.